In this video, we are going to calculate the electric potential and potential energy due to a system of charges. The problem itself is very straightforward, and once you understand this, you'll see how easily you can do a bunch of things. And also, you'll see how it's so much more easier to calculate potential values than electric field values. Okay, so here's what's happening. There are two charges, Q and the two charges, capital Q and capital Q, placed on the y-axis. There is a point P on the x-axis. The distances are shown in the figure. Okay, so y for each of the charges Q from the origin, and the charge or the point P is at a distance little x, okay, lowercase x. So the first question is to find the potential at P due to the two charges on the y-axis. Okay, now what we need to remember is that potential is a scalar quantity. All right, so no need to worry about directions or anything. So to find the potential at P due to the two other charges, all we do is we find the potential due to each of the charges, and we add them up. So this was going to be V1 plus V2. Okay, and we know that the electric potential due to a point charge is given by this equation, Ke times capital Q all over the distance. Okay, now if you look at this picture, the distance of the point P from the charge capital Q, from each of the charges, is simply equal to the length of the hypotenuse there, okay, which is equal to y square plus x square. Okay, and then plus the same thing for the other charge, which is also be Keq over square root of y square plus x square. All right, so this is the potential. Let's add them up. We get 2 Ke capital Q over square root of y square plus x square. All right, now that we have the potential, we can answer the next question, okay, which is very easy once you realize, what's going on. So the question is, what is the potential energy of charge minus Q? Now, what you need to understand is we are not asking for the potential energy of the entire system here. If that were the case, you would find the potential energy for each pair and add them up. We're not doing that. We're only asking potential energy of charge minus Q. So to find the potential energy of the charge, we're simply going to use the relation. So we're going to use the relation Q times V. Okay, and we know what the charge is. The charge is negative Q. Okay, so this is the formula itself. Okay, which is the charge times the potential. And now we're going to substitute. The charge Q itself is minus Q. I apologize for using the same Q's and all that, but I hope you understand what's going on here. 2 Keq, and then divided by square root of y square plus x square. Okay, and this gives us the potential energy as negative 2 Ke capital Q lowercase q over square root of y square plus x square. So extremely easy thing to calculate. Now once you know the potential energy, the next thing you do is we can now also try to answer the question of the speed of the charge at the origin. So before we answer this question, let's understand physically what's going on. If we were to let go of the charge from rest, okay, so let's say it's at rest out here, we let go of this charge, then what's going to happen is that because the charge is negative, because these other two charges are positive, this charge is going to travel all the way, it's going to start traveling to the left. Now, as it moves closer and closer to the origin, its speed is going to increase. Okay, so let's figure out what the speed is going to be. Now, at this point, you should be asking yourself, what concept are we going to use to figure out the speed? Now, if you're thinking about using forces here, that would be incorrect. And the reason it's incorrect is because the force is changing as the particle gets closer and closer to the origin. Okay, because this force is proportional, is dependent on the distances. So it's not constant, it's changing. So you really cannot use force or acceleration and then using, kinematics. So the best idea here is to use the idea of energy conservation. So we can use MEI equal to MEF. And what that tells us is that when the particle is all the way at P, okay, its MEI, we already know it's at rest, so kinetic energy is 0, and its potential energy is negative 2 Keq q over square root of y square plus x square. So we know this. Okay, now this is equal to, now when it's at the origin, it's going to have some kinetic energy, so 1/2 mv square, okay, and it's also going to have potential energy. So at this point, what I would like you to do is pause the video, calculate the potential energy at the origin. okay, just by using whatever we did in parts 1 and 2 of the problem. Okay, calculate the potential energy at the origin, and then come back to this step. So, I'm gonna pause for a second and I'm gonna start, and so here you go. All right, so I'm assuming that you did your calculation and you have the following answer for the potential energy. It should be -2 KEQ over Y, which is the potential at that point, okay, or rather, which is the potential is plus 2 KEQ over Y, but you multiply it by the negative charge and you have the negative sign. All right, so this should be your potential, and now we can solve for V. So let's move things around. We get 1/2 mv square is equal to 2 KEQQ over Y plus 2 KEQQ over square root of Y square plus X square. And then from here we can solve for V. V is equal to square root 2 over M. Okay, and then yeah, we can factor out a few terms, so let's do that. So times 2 KEQQ, and then in parentheses I have 1 over Y plus 1 over square root of Y square plus X square. Okay, so this would be your speed. If you're given distances and stuff, of course you can then plug in the values and obtain results. Now, just a quick note that once you let go of this object at point P, so this is where you let go, okay, and if you allow it to move, the particle is going to accelerate as it approaches the origin, okay, but once it moves past the origin, it is going to start decelerating again, okay, and the reason being that once it's on the other side of the origin, these two charges are going to start pulling it again towards the origin. Okay, so it's going to oscillate, if assuming energy is conserved, it's going to go an equal amount x on the other side, and it's going to keep oscillating between the 2 points. However, the motion is not simple harmonic. Okay, and we'll talk about that, I guess, another time. But the motion is not going to be simple harmonic, it's just going to be repetitive motion. Alright, so hopefully you understand all the parts in this video. In the next problem, we'll do some similar things, but make sure to get all the little details of this particular one. Alright, that's it for this one.